This question came in 2009 for 4 marks in EC Gate. It's a linked answer question, so basically the common data is given here and there are 2 questions to answer. Each carries 2 marks. So let's see the question. Consider a silicon p-n junction at room temperature having the following parameters. So doping on n side is given, which is ND, okay, and depletion width on n side xn, depletion width on p side is given, and Ni is given, intrinsic carrier concentration. This is thermal voltage, which is 26 millivolts. Permittivity of free space is given. This is epsilon naught. This is epsilon r for silicon. Now the first question is the built-in potential of the junction is. So to find the built-in potential, we need KT by Q, which is Vt, ln of NdNa over Ni square. Now we know what is Nd. We got Nd here, but Na is not there, of course, and Ni is here. Okay, Ni is there. How do you find Na? We know this expression that Nd times Xn is equal to Na times Xp. Because Xn and Xp are given, that's why we are using this. Okay, so Nd is 10 power 17 times Xn is 0.1 micrometers, whereas Na we don't know. Xp is 1 micrometer. Micrometer cancel, per centimeter cube. Okay, so then it becomes Na is equal to 10 power 16 per centimeter cube. So if we substitute that values here, we get 26 millivolts times ln of Nd and Na. Nd is 10 power 17, Na is 10 power 16, which is 10 power 33, okay, divided by 1.4 times 10 power 10 whole square, okay, Ni square, okay. So 1.4 square, 1.96 times 10 power 20. So this can be written as 0.026 times ln of, okay, 10 power 13 over 1.96. So let's find this value. 0.026 times ln of 10 power 13 divided by 1.96 is equal to, we get the VBI is equal to 0.76 volt. So this is the built-in potential. So let's see here. So option B, 0.76. Now let's come to the second question. The second question is about the peak electric field in the devices. We know peak electric field is right at the junction, okay, and which is given by Emax is equal to Q Nd Xn over epsilon, or you can take Q Na Xp over epsilon, because Nd Xn is equal to Na Xp. So let's substitute these values here. Q 1.6 10 power minus 19 coulombs times Nd is 10 power 17 times Xn is 0.1 micrometers. See, everything is, this is per centimeter cube and this is not in centimeters, so it is in micrometers. So let me convert this into centimeters. So everything is in centimeters here. Now let's make an observation that when we substitute even epsilon, it is in per centimeter, okay, it is in fact. So epsilon r times epsilon naught, which is 8.854 times 10 power minus 14. So let's find this value. So we'll put 1.6 times 0.1 times the entire powers, okay. So we have 19, 4, 23, 23 and 17. This is minus 23 plus 17, 10 power minus 6 divided by 12 times 8.854 times 10 power minus 14. We can write this 1.6 times 0.1 divided by 12 times 8.854 is equal to 1.5 times 10 power minus 3 times if we cancel this we get 8 here, so it becomes 10 power 8. volt per centimeter, because everything was in centimeters units. Okay, so this can be written as 1.5 times 10 power 5 volt per centimeter. Now here they are asking in megavolts, so let me write this 0.15 megavolts per centimeters. This is the maximum electric field. So these two are not the answers. Okay, now once we find 0.15 megavolt per centimeter, we know that electric field is always directed from N region to P region, because on N region we have positive ions exposed, which are donor dopant ions, and on P side the acceptor impurity ions are negative in charge. Okay, so positive to negative is where the electric field is. Okay, it's not from P to N. So the first option says P to N, which is wrong. So this is not the answer. This is the answer. Okay.